Okay, welcome back to Organometallics. This is day 4 if you're counting. I'll pick up where we left off last time, which is on the SCPR theory. And so the SCPR theory just provides a framework to go from a given coordination number. For example, if you know that you're dealing with a nickel tris olefin complex, then from that information alone, you could propose some reasonable potential geometries. So you go to this table and you see 3 coordinate would be trigonal planar, pyramidal, or T-shaped. This particular example listed, then it would be trigonal planar. The logical undergirdings of this are not so difficult to understand. It's just the minimization of electron repulsion on the surface of a sphere. But this only takes us so far and leaves a lot of unanswered questions, such as how to explain the electronic configuration and the properties that fall out of electronic configuration of a given metal complex, such as magnetism, polarity, etc. So that's where we will pick up this time. And from here, we'll go right into elementary steps, understanding how different coordination complexes react, and then ultimately building towards catalytic applications. So today's lecture will kick off with a discussion of crystal field theory. And crystal field theory is a very useful treatment for understanding the frontier electronic configuration of metal complexes. The idea here is, I think, a fairly simple and straightforward one. If you think about a given coordination geometry and simplify the ligands to point charges, then those point charges will induce a static electric field that changes the relative energies of the constituent d orbitals involved, or the constituent orbitals in general, and specifically of specific relevance, the d orbitals involved. So we know about the concept of degeneracy. All 5 d orbitals are degenerate, but in a static electric field of a constellation of point charges, that does not hold. And so you get breaking of degeneracy. And so the mental model the kind of thought experiment that I want you to engage with here in thinking about this from first principles is to imagine taking this network of point charges. So in the case of an octahedral ligand field, 6 point charges that are at infinite distance away from the metal center, and then bringing those point charges in an octahedral geometry close to the metal center, and asking the question of how the d orbital energies change as a result of that static electric field. And so the metal in this analysis has positive charge. Of course, that makes sense when indeed a metal has a formal positive oxidation state. And if we imagine these point charges coming towards the metal center, then we can appreciate that what will happen is effectively they will run into the individual d orbitals involved to different extents based on the geometries of these d orbitals, and that will lead to a raising or a raising of some d orbital energies more so than others. So those where the running into is most prevalent have higher or push to the highest energy levels, and those where the running into is less prevalent are at lower energy levels. And the extent of splitting, the extent of electronic differentiation depends on a number of factors, including the oxidation state of the metal, the field strength of the ligand, as well as the geometry. So to just complete this thought, ligands with higher oxidation states have a higher extent of splitting. Ligands that have a higher field strength have a higher extent of splitting. Okay, so here's a refresher of what the d orbitals look like. Hopefully no big surprises here. I draw this out ahead of time just so I don't embarrass myself. But really what we're talking about here in considering this thought experiment of an octahedral ligand field is 6 point charges, denoted here with these pink dots, that are approaching the metal center. And what we can appreciate if we consider the dz squared axis is that immediately as these point charges are approaching, we're running into repulsion. And the dz squared orbital has this distinctive lobe as well as the familiar donut. And so there's a high degree of clashing with these point charges as they come in. Same story here with the dx squared minus y squared orbital, because the lobes of this orbital lie directly on the x and y axis, whereas the extent of clashing is significantly less in the dxy, dyz, and dxz orbitals. And so first approximation, we'd expect the dz in an octahedral ligand field, we'd expect the dz squared orbital and the dx squared minus y squared orbital to be pushed to higher energy levels with respect to the other three. And indeed, that is what we see. Let's look into this in a little bit more detail. So first, we can consider the 5 d orbitals that we just mentioned here. One, two, three, four, 5. And then the first thought experiment we'll consider is to apply a spherical field, a so-called barycenter. And what we'd expect here, a perfectly spherical field, is that all of these orbitals that are originally degenerate are still degenerate because they experience the spherical field equally. So that's kind of our concept check there. And then if we want to apply this octahedral field like we just talked about, then what will happen? We will have we said the dz squared and dx squared minus y squared pushed to the highest energy. The other 3 are lower in energy. Note that all of them still are higher in energy than compared to the ground state in the absence of an applied electric field. So again, that's a useful concept check. And then we've mentioned in class that a lot of D6 metals, or a lot of octahedral metals are D6 or vice versa. D6 metals are often octahedral, and so we can fill up electrons, and all 6 electrons nicely fit in the lower energy orbitals, those of T2G symmetry. So what do these labels mean? We have a new labeling system. The 2 higher energy orbitals we call EG, the 3 lower energy orbitals we call T2G. Where do those labels come from? That's a question I've gotten before in class. Those come from group theory. And so for those who've already taken an advanced inorganic or graduate level, advanced undergraduate inorganic or graduate level inorganic class, you will have covered group theory probably ad nauseum. So this terminology falls out of group theory. It's not too critical for what we're going to do in this class, but the EG notation refers to the G part of it is from German gerade, which means symmetric, possessing an inversion axis, and then the E part refers to double degenerate. T part refers to triply degenerate. Again, this is not so important, but if you are somebody who likes to understand the origins of nomenclature, that's the origin of the nomenclature. And then we said the overall splitting energy here, we're going to use the Greek letter. Oh, I already have it to the right here. We're going to use the Greek letter delta and refer it to the octahedral ligand field, so delta oct. And then we can break this up into the 2 constituent components. And you see that the top 2 are, again, higher in energy, and they account for 6/10 of the overall splitting energy, whereas the bottom three account for 4/10 of the overall splitting energy. Another question I've gotten in class over the years is what is this the splitting energy actually translate to in terms of for a, let's say, representative metal in terms of real energy values that we can appreciate. And of course, that can be read out by understanding the light absorbing character of a given metal complex of interest. And so you can test that experimentally and then do some back of the envelope calculations to convert it into electron volts or kcals per mole, and that's done here for you. And then we can apply this analysis to all the different geometries that we have encountered, the ones that are most important, are most commonly encountered in this class, as we said, are octahedral, tetrahedral, square planar, and to a lesser extent, things like trigonal planar or trigonal bipyramidal. So here's the resulting orbital diagram that results from a tetrahedral crystal field. And if you think this through, then you'll recognize that in a tetrahedral field, there's not as much running into as there is in an octahedral field. So the overall extent of splitting energy is diminished. It's less than half of the splitting energy in an octahedral field. And one thing that we have we mentioned briefly is that some of the d-electron counts that are commonly observed in tetrahedral complexes, and so we can just play this out. Let's consider the case of a d5 metal, and then we would fill up first using the Aufbau principle in combination with Hund's rule, and we'd find we have a choice actually. So you see what I did just then was to fill up according to Aufbau first and Hund's second, but the other way to do it would be to do Hund's first and Aufbau second. And so the extent of splitting energy here dictates how you will fill up these electrons. And so this would be a case of d5 high spin, quote unquote high spin, where the splitting energy is low. And then what I drew the first time would be the alternative, which would be considered low spin. And so you have this competition between, yes. Oh, aging.
Sorry, how do we know if something is high spin or low spin?
We'll talk about that. It depends on the strength of the, it depends, falls out of the splitting energy. So we just introduced the concept that splitting energy depends on several factors: the metal, its oxidation state, the ligands, the nature of those ligands. And so we'll try to build up an intuition for this as we proceed through today's class. And so again, there's this consideration of the energy required for pairing two spins versus the energy required for going to a higher energy orbital, competition between the Aufbau principle and Hund's rule, and which of those two considerations wins out is what determines whether something's high spin or low spin. Tetrahedral complexes are often, but not always, high spin. So let's consider now square planar. And so if you think about square planar geometry here, there's an intimate relationship between square planar and octahedral geometries, namely that the two ligands that lie in the z-axis are absent. And so the orbitals that are most principally involved with interacting with those ligands, their energies change most dramatically. And so you see the dz squared orbital goes much lower in energy, whereas the dx squared minus y squared orbital retains its relatively high energy. And then the orbitals, I think there's a typo here, the orbitals that have some Z character, like DXZ and ZYZ, DYZ also go to lower energy because of the lack of these Z ligands. One example that we can consider as a class is one of our, in this department, most favorite and commonly encountered square planar D8 metals, and that is palladium acetate. And so maybe I can pose this to someone in Jin's group. Anybody want to take a stab at this? I see Eugene volunteered Will. So Will, we use this formula, palladium acetate, when we're massing out our 2.2 milligrams of palladium acetate for our screening. But what is palladium acetate in reality? Is it as drawn here?
Of course not.
Of course not. So what is the reality? The reality is more complex.
More accurately, it's I believe it's more of a polymeric structure of bridging acetate.
Multi-metallic, and the most commonly used brick red form that we see is typically trimeric. There are other, as you said, other oligomeric and multi-metallic states. And so then there's this question of how do you, if the metal wants to be square planar and you've got three of them to fit around this, fit within this, this trimeric structure, what would that look like? And so I'll give you 15 seconds to think about that. And then so that I fumble with this, I drew this out in advance. So shame on me. Although then when I actually look at this, I think if I drew out in advance, I probably should have done a better job, but then it looks something like this. So each individual palladium-2 is happily in its D8 square planar, D8 electronic configuration, square planar geometry, and all three can be accommodated without significant strain. And we said that D8 electronic configuration, D8 electronic configuration is common for square planar complexes. So let's just do that exercise then and fill in the electrons. And so then by convention, the splitting energy is defined as the energy between the dxy and dx squared minus y squared orbital, because square planar geometry is so common for D8 metals. But you could define it alternatively. For example, if you wanted to define it this way, is the splitting energy, you could do that as well. Okay, now we're going to build towards an answer to Eugene's question about how we know whether a given ligand set, a given metal has a high amount of splitting or a low amount of splitting. And to do that, we'll introduce an empirical trend called the spectrochemical series. I want to emphasize that this is an empirical trend. This doesn't fall out of divine principles. And this spectrochemical series, the ordering, so what the spectrochemical series is it's an ordering of ligands on the basis of their splitting energy. And this can be, as you can imagine from the name, where does this come from? It's ultimately read out of electronic read out of absorption energies. And so out of these types of experiments comes an ordering of splitting energies. The precise relative ordering depends on the nature of the experiment, namely the metal that is used and the oxidation state of that metal. So if you, in a previous class, learned a slightly different ordering, that's probably because that ordering is derived from a different metal in a different oxidation state. And the ones I'm showing here are those derived from cobalt, the classical. So you can collect data for a spectrochemical series as a function of the ligand, and then you can do the opposite, where you keep the ligand the same and collect a spectrochemical series as a function of the metal. And that is shown here. and one of the trends you'll notice is that, again, higher oxidation state metals have higher splitting energies, as I mentioned previously. And then the exact ordering of the metals, you can read here for yourself. Later transition metals, those that are farther right on the periodic table, in general, have higher splitting energy. So higher oxidation state, and then the other trend is that when you go down a group, there's higher splitting energy. So this is one of the reasons why the most commonly observed high spin metal complexes that we see on planet Earth are those from the first row, because second and third row metals in general have higher splitting energy. So that the cost of going to start populating these higher energies is much greater in a second or third row metal. Okay, so we introduced briefly this concept of low spin and high spin, and now we'll define that a little bit more formally. Okay, so we're going to consider iron 3. We know, since we've been studying the periodic table, that iron 0 is D8, iron 3 thus is D5. Octahedral ligand field. And we can consider two cases: the iron nitrite hexanitrite complex 3- and the iron hexabromide complex also 3-. We can go to the spectrochemical series that we just introduced and see, okay, bromide is certainly on the left side. Nitrite is somewhere kind of in the middle, but I've given you this clue that one is low spin and one is high spin. So maybe if you hadn't been told a priori which was which, it might be difficult, but you can consult this ordering, and then you can consult the ordering below and say, okay, iron's in its high oxidation state, +3 probably is relatively high splitting energy, so that we'll go ahead and call that high enough splitting energy qualitatively to define it as low spin, and then we can fill in electrons. All 5 in the T2G orbital. And then when we have this the opposite scenario where the splitting energy small, then when we fill in electrons, Hund's rule is going to be overruled by the Aufbau principle, and we will fill into the EG before we do any backfilling of the T2G. So this is the competition. Aufbau principle dictates that lower energy orbitals should be completely filled before filling higher energy. And Hund's rule is that if 2 or more orbitals with equal energy available electrons will occupy them singly before filling them in pairs. And then a closely related concept that you will hear if you attend any kind of inorganic chemistry lecture is terminology like diamagnetic and paramagnetic. And I don't know if anybody has a good mnemonic for remembering which is which, but because I never learned a mnemonic, I just had to force my brain to remember that paramagnetic complex means no unpaired, sorry, a diamagnetic, see, I already got it mixed up. Diamagnetic complex means no unpaired electrons, paramagnetic species means unpaired electrons, and the consequences of this is that when you have unpaired electrons in your complex of interest, you often have difficult time characterizing that using some of our favorite techniques such as NMR. Yes, Srigut.
Sorry, can we go back to the nitro versus bromide example?
Of course.
All right, can you explain one more time why, based on the trends that you we know that the nitro group is low spin and bromine is high spin.
Well, I think, let me answer this in a slightly different way. If you were in an exam, you'd be given an extreme case. I think we would try to, or if it was a borderline case, we would say, entertain both possibilities and walk us through your reasoning why you would favor one versus the other. But because these are just empirical trends, it's not always obvious a priori. In this case, I hope it's obvious because I just told you one was low spin and one was high spin. But you would consult the spectrochemical series. You would first see that it's relatively high oxidation state. You'd see that iron is towards the right. And then you'd see that nitrite is kind of in the middle. And so maybe on the net, this is a relatively large splitting energy. And again, in terms of the logic of this comparative example, you're just comparing one thing to the next. And bromide is definitely a low field ligand. So by the nature of the comparison, the nitrite is going to be a higher field ligand. Now, this would be even less ambiguous if we had a, hexacyano iron 3, then you'd say, okay, that's very clear cut. And we'll look at a complex that's kind of similar to that and the problems, but that's the logic that you should be. Yeah, Sam.
Back to the plating.
Of course.
So here, we're treating the orbitals on the left as like d orbitals.
Yes, it's palladium, so it should be 4.
Or
yeah,
and it would still have the same annotation as a 3D orbital.
yeah. Whether you're so for crystal field theory analysis, remember that and we'll see the connection. It's a very deep question that you're asking. There's what crystal field theory allows you to get a snapshot of is the frontier electronic orbitals, and what that snapshot looks like doesn't really change whether it's 3D, 4D, 5D. Now, the absolute values of those energies, of course, does change because you're at a higher principal quantum number in the case of 4D compared to 3D. But the relative picture, which again, this is just a all qualitative description at this point, stays the same. That's a really thoughtful question. Okay, so let's engage then in this kind of question that everybody has been grappling with. And to do this, we'll go to problem of the day number 3 from last time's worksheet. So if you don't have last time's worksheet, I will go ahead and do a share. I can. So the exercise here is to predict using what we have talked about before up until this point, whether something's high spin or low spin, or if you're not sure, that's okay too, and we can talk about why you're not sure. For cobalt hexa-aqua complex, number 1, cobalt hexafluoride complex is number 3, and then this nickel tetra cyano complex is number 2. So take a minute to jot down your reasoning. All right, Catherine, what do you have? Hexa aqua, Catherine's vote is high spin. And then we can jump to C because that's most closely related. What did you have for that?
Here,
Yes,
there is the overlap in room reservation. So let me go to the lab and
oh, sorry, you can join from Zoom if
Yes.
it's more
yeah.
convenient for you.
yes,
Sorry about that.
sorry.
We'll get that sorted out. Okay, so C you said was. Okay, high spin, but then you seemed less sure about that one. So what else were you thinking about? So the metal stays the same. What changes is the weighting. Okay. And B? You said low. Okay. Anybody get anything the same or different? Any different answers?
Yeah, I got low, high,
High.
yeah, just because H2O is a weaker.
Oh, high for which one?
Sorry, yeah, so low and then high. So A is or B is high. That's the A is low.
Okay, so sorry, so you had low, high, and then what was
High.
it? Low, high. Oh, okay. What do we think as a class about this? Yes, Amy,
Oh, I was gonna say, I got low, high.
you got low, high. Okay,
I don't know. You have low, high, also.
low, high.
Well, for nickel, you can't even really, there's not another alternative way to draw it, right? So there's like no low or high spin configuration. There's just one.
Well,
It's D8.
but then you picked a high spin. For.
Yeah, I know. I mean, when I say high, it just means unpaired electrons,
I
but
see.
like regardless, there's not another way to draw it. Right? Like there's not another way to populate the orbitals with the D8 on octahedral. You're always gonna have two unpaired.
Well, you can, if it's D8, you can draw it like we did for palladium, or you can draw it.
Oh, it's square planar. I
Yeah.
thought it was octahedral.
Okay, so this is bring up a lot of good discussion. So let's do our initial due diligence first. So let's consider A and C as a pair. So as a good starting point is always to just do our electron counting. Cobalt 0 is D9, so cobalt 3+ is going to be D6. So immediately we should be thinking D6. We're likely in this octahedral zone. That makes sense. Each of these has 6 ligands around it. They're likely going to be inner sphere. So we know that the electronic configuration is going to look like this. And so we really have two kind of options. Got one that's going to be high spin, low spin, and then we can. All right, I did that backwards. Right, sorry. So these are our two possible answers. And so again, using the terminology we just defined, then the left one would be diamagnetic, right, would be paramagnetic. And so what you're provided here, you're not provided a lot of information. So you just have to make a judgment call. You look at, you see cobalt 3 is pretty far to the right on this spectrochemical series in terms of metal. And then the two ligands are pretty, in the middle kind of. And so I think you could make a conclusion that because of how the problem is designed, if we're asking you to make a comparison, then maybe you would say that that this one is low spin. And then this one, if we just have to make a comparison, is high spin. But if you also came up with low spin for that, then I wouldn't fight you too much on that. And then the nickel one, we said nickel, we're gonna do the oxidation state and figure out nickel's +2. That means it's D8 square planar. It's nickel in the +2 oxidation state, which is pretty far on the left. I guess you could also entertain the possibility that it's tetrahedral if you want and do that thought exercise, but and then you have cyano, which is one of the highest field ligands. So, again, you just need to make a judgment call and you'd say maybe these cyano ligands, which are really high field strength, maybe we just call this low. Yeah.
It's supposed to be T2 G instead of T2 T.
Thanks.
And the other one had high speed.
Okay, so if that is unclear at all, then we'll do some more examples. Again, just try to reduce it to first principles. And sometimes in these types of questions, you're just asked to make a judgment call. And if you're on an exam, you're not sure, just explain your reasoning based on what you've been taught, and that's a good rule of thumb. Okay, let's consider now problem of the day number 4. And this combines two things that we don't like, which is or two things that we're trying to learn on the fly, which is this high spin, low spin, ligand field strength analysis, and then our dreaded nitrosyl ligand. So to read the question here, this interesting iron nitrosyl, the crystal structure was solved in the 1960s. The geometry is a distorted octahedral. So first approximation is octahedral geometry here. Proposed oxidation state, binding mode of NO, and then whether the complex is high spin or low spin. And then a question that's going to foreshadow what we'll talk about for the rest of the class is the extent of back bonding into the cyano ligand versus the nitrosyl ligand, and how you might determine that. So there's a lot to unpack here. And I think just for the purposes of the exercise, because this has come up a few times as a question, we can do this both ways, whether we want to consider linear or bent nitrosyl. You don't know from this question and the information that's provided what might be happening. So we can just entertain both. So let's first consider the linear case. Al, what would you have here then? Or iron oxidation state? Oh, I didn't. Oh, I thought Al was back there. Okay. What about E out?
So for cyanide group is -1,
And we have a total charge of -2. It's more happy for iron to be +2, but not +1. I guess NO is +1 and oxidation state of iron is +2.
Okay, so that'll give us D6. And then you also kind of alluded to the other one. So we're talking about the linear, but you said, so this is the case where the linear is the case where the NO is counting as a plus ligand. The other alternative, if you consider this just an X-type ligand, then you're going to get to iron +4, E4, right? And so these are the two ways you could consider this to be. And now one hint here in the question is that the geometry is an octahedral. And so we know that general D6 metals like this octahedral geometry. So that maybe is one signaling element here. But again, if you're asked this on a test for homework and you weren't sure, then you can just do it both ways and see where that takes you. Okay, so then which one do you prefer here? You said you prefer the linear. Yeah, okay, so we can just play that out then. And then would you think this is high spin or low spin?
Low spin.
Iron 2+, and then you've got a bunch of cyanoligands and an NO ligand. So you're thinking those are all pretty strong fields and you prefer low spin. And then this last part of the question, just staying with you, Eo, what would you expect is better at back bonding? So back bonding here, we're referring to the d orbitals on the metal that are filled. We see this at D6, so there are electrons in these kind of quasi non-bonding d orbitals, and they can donate electrons into a pi star antibonding orbital on the CN or NO ligands, as we will talk about. Which of those do you think is a stronger acceptor intuitively?
Probably yes. Cyan.
The cyano. Why do you like the cyano?
Because yeah, both of them are like vice versa to the nitrogen gas, but we have more positive charge with NO+. Ligand. So I think it's a little bit hard to hydronate electron to the metal. Probably Cn- is more strong.
What, in general, what would you expect is a better magnet for electrons? Something that's negatively charged, something that's positively charged?
Vacuum.
What do you think wants electrons more? Something that's positively charged or positively charged? Okay, so there are different ways to reason this, but for me, as I was thinking about, I know it's linear. I know that the way that we think about this is as this positive. I would say that probably wants electrons the most, and so that might be the better back bonding acceptor. How would you test it if you wanted to? I mean, we could disagree on what the answer is, but ultimately you could run the experiment. And so what would be the experiment? We can crowdsource this one, yeah.
So I forgot the energy of the seal. CN.
Oh, I think you got it. So you could turn to, if I'm thinking IR, stretching frequencies. Between free and bound CN versus NO, right? And so if the NO stretching frequency goes way down in wave number, that means there's a higher amount of back bonding. And we'll see this if this is going over your head, then we'll unpack this. But that is, I think, a first approximation, good way to do it. Yeah, Eugene.
Sorry, just a question about the electron counting for the
Yeah.
bent. If it's bent, wouldn't that mean it's, let's see, an X type ligand? So then you'd have, I think, 6 X type ligands, 2 electrons. Does that come out to 4?
Exactly. So you've got 6 in this case. In the bent model, it's 6 X type. And then the overall charge of the complex is -2. So that means the metal, so the ligands are bringing -6. The overall charge is -2. So that means the metal's got to bring +4 for the arithmetic to work out.
So then wouldn't that make linear +3? Or am I?
Linear, yeah, it's a great question. So linear NO, remember, has this unusual property that it's a L type, but has a plus charge.
I see. Okay.
All good? Yeah, thanks. Those are great clarifying questions. So let's jump in now to let's see, a few more details about structure bonding. So another concept I'll introduce here is that of Jahn-Teller distortion. And we use this terminology of a distorted octahedron. And so that foreshadows this kind of principle of Jahn-Teller distortion, which is a phenomenon of spontaneous symmetry breaking. This occurs whenever degenerate orbitals are unequally occupied. And why does it happen? It happens so that the metal complex can settle its way into a lower energy state. And so as you can imagine, when you have this unequal occupancy of orbital degeneracies, unequal occupancy of degenerate orbitals, the metal complex can adjust its geometry slightly to adjust the orbital energies to make the occupied one a little bit lower and the unoccupied one a little bit higher, so that it's carrying its electrons in the lowest energy orbitals possible. And that is indeed what happens. So let's consider the case D7 low spin metal complex. A perfect octahedral geometry adheres to the rules we already talked about. We fill in the T2G and then the EG orbitals, but it can distort itself into square bipyramidal geometry by allowing the 2 axial ligands to, the bond length between the metal and the axial ligands to increase slightly. What does that do? That stabilizes the DZ squared orbitals to an extent because we're pushing those point charges farther away in the crystal field theory analysis, and destabilizes the dx squared minus y squared. And so that's the crux of it. Any questions on that? Okay, now what I'll introduce now is ligand field theory. And the high level way to think about ligand field theory is it is the superposition of crystal field theory and MO theory that you learned in your undergraduate Orgo series. And I will say that ligand field theory, if you were to take a graduate level inorganic class, you would get a really heavy dose of ligand field theory. Ligand field theory, if you are up to date in your readings in Crabtree and Hartwig, you'll see that this is not extensively covered in either of these textbooks. And so, any class, we talked about organometallics can be capital O or capital M. This class is kind of a capital O organometallics, but if you want a capital M organometallics class, you can walk over to UCSD and you have as much ligand field theory from my good friend Josh Figueroa as you like. So I won't go too deep into it, and what I present you might already find too deep, but I just want to paint a picture that there's this higher level treatment. The higher level treatment allows you to actually, in many cases, simplifies into the crystal field theory treatment. And so that's going to be sufficient for most of our purposes. And then we can kind of zoom in on particular MO theory interactions that are relevant to the discussion. And so why we need this is because we've talked, all of the crystal field theory analysis so far just treats these ligands as point charges. But of course, that's a vast oversimplification. We know that the electronic properties of a pure point charge, like a hydride ligand, versus an olefin ligand that can engage in more complex bonding is very different. And so that's what ligand field theory allows us to rationalize, this difference between point charges and reality, which is that ligands can have multiple types of bonding interactions. So to introduce ligand field theory briefly, I need to introduce this terminology of symmetry adapted linear combinations of atomic orbitals. And these that are abbreviated SALCs. And SALCs can be thought of as analogous to how we build up molecular orbitals from atomic orbitals. It's not exactly the same, but it is very much analogous. So we have these constituent orbitals, and in this, all we're going to talk about here is the simplest case, which is pure sigma donors. So what we do here is we combine this, and we're going to look specifically at the case of an octahedral geometry. So we combine these pure sigma donors in different linear combinations. And then again, through group theory, we arrive at these 6 SALCs. And again, if this feels unfamiliar, just lean back on your familiarity with MO theory and think, okay, yeah, atomic combinations of atomic orbitals get molecular orbital. This is a combination of atomic orbitals or of ligands approximated as sigma bonding interactions for symmetry adapted linear combinations. And I think I want to try to make this as intuitive as possible. You don't need to think too deeply other than to just look at these SALCs and say, what orbitals have I ever encountered in my career in chemistry that look like they would nicely overlap with these SALCs? And you'd look at the A1G and you'd say, that looks like it would overlap nicely with S orbital. You'd look at the T1U and you'd say, that looks like it would overlap nicely with p orbitals. And you'd look at the EG and you'd say, those look like they would overlap nicely with the, let's say, Z squared and dx squared minus y squared orbitals. And that's the extent of the analysis that you need at this point. Just looking at them and recognizing some similarity with the shapes of orbitals that you are already familiar with. Okay, now we're going to dive a little bit deeper, but I just want you to keep that connection to your intuition about the orbitals that you know and love. So let's now take a deeper dive, although hopefully not too deep, into a specific example. So we're going to consider this titanium hexa-aqua 3+ complex. So anybody want to quickly do a d electron count on the fly for this one? B1, okay, so you're saying, and what was your reasoning there, just so everybody's on the same page?
It's aqua is neutral, and it's the overall complex is +3. So titanium 0 is D4, so -3 is.
Okay, so this is D1. Okay, so let's walk us through how these SALCs that we just constructed above are going to interact with the corresponding d, s, and p orbitals of the metal. And so the first thing to appreciate is that the orbitals on the metal are higher in energy than the SALCs. Why? Because they're at a higher principal quantum. And so we had said that the T1U orbitals are nicely going to overlap with p orbitals, in this case 4p. We said A1G orbitals are going to nicely overlap with s orbitals, in this case 4s. And then we said that the EG are nicely going to interact with the dz squared and dx squared minus y squared. And so we can just draw those now molecular orbitals. And they have the bonding component, and then they have the anti-bonding component. And the other d orbitals, the dxy, dyz, and dxz orbitals, they don't really overlap nicely with any of those salts that we introduced. And so they're going to be kind of the non-bonding component. Now the Eg is going to have its bonding component, and it's sorry, I said non-bonding. What I meant is antibonding. It's going to have a bonding and antibonding component, and so that we represent as such. And so look what happens, look what falls out of this. We have a frontier orbital picture that looks very much, should hopefully look quite familiar. We can just zoom in on this. And what we see is a picture that very much is similar to our crystal field theory treatment of a octahedral metal that is D1. And then you can imagine, and we won't do this, but you can imagine how when you go from this case study of a pure sigma bonding ligand to a more complicated ligand, like a CO ligand that is also engaging in back bonding, how things get more complex more quickly. But if you stop and thought about it, you could still very much work your way through that. We're going to look at MO interactions often, but in a slightly more simplified way than every time drawing out this type of orbital depiction, because that would be very painful for everybody. So to talk about bonding, we're going to introduce the different types of bonding. And remember that this terminology, sigma, pi, and then one that we'll introduce very briefly, delta, has to do with the symmetry of the orbitals that are involved in forming the bonding interaction. And so in direct analogy, direct connection to main group bonding, we know that a sigma bond is going to be composed of two lobes of the same symmetry overlapping between one metal centered, one ligand centered. And so we can consider some cases here. The lone pair from triethylamine or any tertiary amine will donate into an unfilled orbital on the metal. So think here, dz squared, dx squared minus y squared. And there's some terminology that can be kind of confusing because ligands that are themselves pi bonds can still engage in sigma bonding interactions with the metal because of how the bond is defined, that these are all the same symmetry of the overlapping lobes. So that's the sigma bonding interaction. And then there's a pi bonding interaction. Many ligands will, in fact, exhibit pi bonding, and there are two flavors of pi bonding. There's the first I'll introduce, we would call pi donors. And pi donor ligands are those that have lone pairs on the ligand, even when coordinated to the metal. So they have one lone pair that's engaging to bonding to the metal, and then they have another lone pair somewhere on the ligand that can engage in further bonding. So let's consider chloride as an example. One lone pair from chloride forms a bonding interaction with the metal, and then and then an empty d orbital of appropriate symmetry. So if if the bonding interaction here is with dz squared or dx squared minus y squared, then an empty dxy, dyz, or dxz orbital of appropriate symmetry can form a further stabilizing interaction with one of these lone pairs in what's called a pi donating bond, donation bond. And then the other flavor of pi bonding we would call pi back bonding or pi accepting. And this takes place with a number of different ligands: olefins, CO, phosphines, and so on and so forth. Let's first look at the case of olefins. So the filled pi bonding orbital of the olefin is serving as the sigma donor. And then the pi star antibonding orbital, if you just zero in on that, you would look and say, aha, that's appropriate symmetry where a filled d orbital on the metal, dxy, dyz, or dxz, provided the metal is not d0, if it's anything above d0 and has electrons sitting in these non-bonding d orbitals or orbitals of predominant d character, predominantly metal-based orbitals, can engage in pi back bonding. We talked about how over the this type of bonding interaction was pinned down and now is known as the Dewar-Chat-Duncanson model. The consequences of pi back bonding are that the metal ligand bond gets stronger. And that makes sense. You have one bonding interaction, you have another bonding interaction that starts to almost look like a double bond. So that bond is getting stronger. But at the same time, you are populating a pi star antibonding orbital. And in so doing, you are weakening that bond. And that can be read out by looking at, for example, an X-ray crystal structure of bound versus not bound olefin ligands and seeing the extent of elongation in the bound state. Phosphines are an interesting case because they also, and we'll consider the case of triphenylphosphine here, they also engage in pi back bonding, but they do it in a sort of sneaky, subtle way. So first we can appreciate that phosphines are very strong sigma donors by and large, because they have this juicy non-bonding electron pair that is it's a relatively soft motif. It's forming a strong sigma bonding interaction, but at the same time, it can serve as a pi acceptor. How does it do that? Well, at first glance, you might think that it's this unfilled 3D orbital on the phosphine, and you wouldn't be wrong in thinking that. But if I told you that wasn't totally right, then you might second think, okay, maybe it's the sigma star antibonding orbital of the phosphorus aryl, or the PC bond. And there I would say you're also not totally right, but in aggregate, you are right, which is that it's an orbital mixing model. So you have the 3D and PC sigma star that engage in this orbital mixing model. The orbital involved looks like this, and you can appreciate that it is of appropriate symmetry to engage in back bonding interaction with a filled d orbital on the metal.
Agree?
Yes, so if you have learned in a previous class that it's just the PC sigma star or it's just the 3D, that's not totally wrong, but it's just a little bit more complicated than that. Yeah, Eugene and then Rico.
So which antibonding orbital is it exactly that the metal's donating into in that case?
The PC
Like
sigma
which,
star orbital,
which C?
one of the aromatic.
Oh, okay. So is it just any of them or like an aggregate of all three or?
An aggregate of all three, which is what I've tried to represent with this orbital mixing model depiction.
Right.
Other important back bonding interactions to have some familiarity with includes molecules like CH bonds or H2. H2 is a little bit simpler, but the situation extends to interactions with CO bonds as well. And so these are called sigma complexes. This is related to a term that you may also encounter, which is called a agostic interaction. We will talk about this more later, but agostic interaction are kind of chelated or quasi-chelated structures. Sigma complexes are those where the ligand is freely diffusing otherwise. So we can appreciate that H2 has the sigma bonding interaction, and there's electron density between the two H atoms, and that can then serve, that filled sigma bond can serve as a sigma donating ligand to the metal. And then if you draw out the pi star antibonding orbital and orient it with the appropriate geometry with respect to the metal, you'll see that it is also capable of engaging in pi back bonding. We talked about how you can read out the consequences of back bonding, and that can be done as well in the case of an H2 metal adduct. And so if you were to perform X-ray crystallography of an H2 metal adduct, and this has been done before, you'll see significant elongation compared to the bond of free H2. Now, this itself is not trivial, because one of the things you would appreciate if you've done any small molecule crystallography is that hydrogen atoms do not diffract X-rays strongly. So what you're really talking about here is a single crystal neutron diffraction experiment, which you can do. You just need to have a hookup at a synchrotron. I've done this actually. I did this during my PhD. It's quite an experience. But these are not routine sorts of measurements. So you can imagine the work that went into just testing and verifying these types of sigma complexes crystallographically. And then if we take this to its logical extreme, we say, okay, what's really happening here? We're engaging in back bonding. We are populating a sigma star antibonding orbital. What if we just take that all the way? Then what happens? Then you break that sigma bond, and you indeed form two new bonds between the metal and the H, and that is an elementary step called oxidative addition. So it's a continuum here, but if you continue populating a pi star antibonding orbital or sigma star antibonding orbital, then you will get oxidative addition. COs are a really important class, and I think Anna alluded to why they're important, which is that they are in the perfect region where you can use IR as a readout for the extent of back bonding. So CO effectively is your beacon, and you look at the CO stretching frequency and you can infer something about the electronic properties of the metal. So let me unpack that here. CO has its lone pair, which is engaging in sigma bonding, and then this pi star antibonding orbital has two pi star antibonding orbitals that can engage with as pi accepting ligands. Upon forming that back bond with the filled d orbitals of the metal, it weakens the CO triple bond. So it's a triple bond in its free state and the bound state. It now loses triple bond character and is some kind of hybrid between a double and a triple bond. And so we all are familiar with that if we have from our orgo classes, the carbonyl ligand, carbonyls in general have really distinctive stretching frequencies that are, let's say between 1600 and 1750 wave numbers. And so one way I like to think about this is as you engage in stronger and stronger back bonding, the metal carbon bond has starts to adopt more double bond character, and the CO bond starts to look also more like a CO double bond than a CO triple bond. So as you go in this direction, more and more back bonding. You start to push like 1900 wave numbers in terms of IR as you go this way. It just looks almost like free CO. And that's the crux of why CO is a useful ligand in terms of understanding the electronic properties of the metal. And the CO's, the dissociation energy of a bound carbonyl, you can imagine, varies greatly depending on the extent of back bonding. So of course, when the metal ligand bond has more double bond character, it requires more energy to dissociate it. And then there are several isoelectronic ligands. We've covered nitrosyls, ligands that are isoelectronic to CO and have similar utility. We talked about nitrosyl, also N2. Josh Figueroa, one of our guest speakers, is an expert in these types of isoelectronic series and has been one of the first to document the isostructural nature of BF actually as a ligand. And then, bless you, a corollary to everything we've talked about is that if to engage in high back bonding, not high forward bonding, but high back bonding, you need d electrons on the metal. So if you do an electron count and you get to d electron count of 0, that is not going to engage in significant back bonding. Okay. We jump to a different set of slides here. Okay, let's jump into start talking about how structure and bonding will manifest in terms of elementary steps like ligand exchange. And to do that, we will take a look at problem of the day numbers 1 and 2 from the day 4 worksheet. I'll do a quick share in case you don't have your sheet handy. We'll do these back to back, so take a minute to think about it. First, 2 related looking structures, zirconium olefin complexes. And I want you to make a prediction about which of those 2, the left or the right, is engaging in stronger metal to ligand bonding. And then, if that's easy for you, then I would ask a follow-up question, which is how would you know, or what analytical technique might you use to test your hypothesis about which is engaging in stronger bonding? Question number 2 is about, it's foreshadowing some of what we will cover with ligand exchange. And it's asking you to consider the equilibrium between a tetra-coordinated, tri-coordinated nickel center with various phosphine/phosphite ligands. And asking for each of these ligands where you might expect the equilibrium constant to lie, and then to rank them. And this, like some of the other questions we have had so far, is not meant to have a completely cut and dry answer. You'll have to make some judgment calls on this. So different people might have different answers, and that's okay, based on the information that's provided. All right, Mike, which one do you like here?
The left.
You like the one on the left? Okay, why?
You have increased sigma donation from the methyl to the zirconium center, which puts more electron density on zirconium, which means it can do more back bonding.
Sorry, just give me a minute to adjust my screen share.
I guess I was thinking about around zirconium 3 versus zirconium 2, right?
Okay, let's just play this out quickly. So let's do a quick electron count on both of these, just so we're grounded in the basics. So you said on the left,
Yeah, I'm
do
gonna
our-
reverse my answer on you. Just
Okay,
yeah.
that's fine. So let's just do a quick electron count. So we've got zirconium, we've got 3 X-type ligands here, CP, CP, methyl. It's overall +1. So what is the oxidation state of zirconium?
4.
Zirconium +4. On the periodic table, what group is zirconium in? I can't remember. I think Alex flashed a 4 for you.
Yeah, 4.
4, okay, so then what would the d electron count be?
0.
D0. Okay, and then let's do the one on the right. Here we have 2 CPs, charge neutral, so we're gonna have D2. And then you said you were gonna reverse your answer and pick the one on the right.
Yeah.
So here you're saying that, if I understand your reasoning, you have more d electrons in zirconium. It's also +2 as opposed to +4. So there's just more electron density. It can engage in more back bonding. Back bonding will strengthen the metal ligand bond. That makes sense. And then to make matters worse for the complex on the left, look, it's D0. So they can't engage in back bonding at all. So that's going to be a pure single bond. So did anybody get anything different or have questions on that one? Thank you, Mike. Riku?
No.
No, okay, sorry. And then a corollary or that follow-up question I asked to people in the class, how would you read that out if you wanted to actually test? Kevin, you have an idea?
You can look at the CC stretching and IR. So if it's stronger back bonding, it should be lower ground state energy, which means lower frequency of vibration.
Okay, I think that's reasonable. A lot of times that's less commonly used for metal olefin complexes because that stretching frequency just comes in a crowded part of.
It's usually for CO, right?
For CO, yeah. Riku?
Can you do an X-ray and get the zirconium?
What would you expect to see?
Stronger is shorter.
So when you have engaged in back bonding, again, let's just take back bonding to the extreme. Let's imagine this thought experiment. What if this is a super back bonder? Then it can even have metallocyclopropane character. And then you can read out a couple things. You can read the length of the CC bond. You can read the length of the zirconium olefin bond. So I think that is a reasonable way to do it. Or based on how the question's asked, just which is a stronger ligand, you could titrate in some kind of competitor ligand and just see when you get displacement of ethylene. Okay, all very good. Yes.
I have a
Yeah.
question. I wonder if that possible to distinguish them through HNMR because like a double bond connected hydrogen has a higher chemical shift. Is that possible?
Yeah, I think you just have to be cautious with using proton NMR as a readout for electron richness in general. There are some cases where that does not track with the electron richness. And I think people will sometimes use carbon NMR as a slightly better tracker. And so in this case, carbon NMR, you could see the extent to which it's sp3 versus sp2 hybridized, and that might allow you to read out the level of back bonding as well.
But also argue that the second complex may be paraben based on its spectron configuration. It's probably good.
Okay, problem of the day number 2. This one is tough and open-ended. So any thoughts are welcome. I'm 100% sure that there are at least 5 different rank orders here. So let's just get one down and then we can discuss. Alex, what did you get for this one?
I think, I mean, I don't have like a full order, but I have like some comparisons between some of them.
Okay,
So
what if I forced you to do a rank ordering?
force me to do a rank ordering in increasing AD, I would say I would say 3 1, 2, 4, 5.
Okay, and what is your rationale?
So my rationale is to a first approximation, I'm just looking at the atom that's directly connected to the phosphorus. So if that's more electronegative, then it's a better back bonder. And so it should bind more strongly and be less prone to dissociation.
Okay, so you're using pi back bonding as your predominant
So I guess
guider of this trend.
yeah, so
What would,
I guess for the triphenylphosphine, then I kind of look at the spectrum. But
Yeah. well, you're saying that it's the, in this analysis, the worst back bonder?
yes.
Yeah, and that's right, I think.
But then I think there's also sterics. as
Okay.
well. So at least between like 1 and 2, I would say 2 dissociates more because it's more sterically hindered. And you'd get I guess a happier 3-coordinate complex.
Okay.
And then the same between 4 and 5. Those also, it's like there's a little bit of electronic difference with the aryl substituent as well.
Let's get one more volunteer who had something different. Eugene, what did you have?
I would say 4, 5, 1, 2, 3.
Okay, and how are you thinking about it?
I was thinking about it in terms of the PO antibonding orbital stability. So I assume that the phenoxy radicals or for phenoxy anions from 4 and 5 would be more stable than the anion oxyanions of 1 and 2, and then 3 I assume would be a carbon anion, which would probably be the least stable. Meaning that the antibonding orbitals of 4 and 5 are probably more accessible than 1 and 2, which is more accessible than 3.
Okay, yeah, I think the so you're making also a pi back bonding argument, but just thinking, maybe giving different rationale for why you might expect different phosphites to be better or worse back bonders. Is that a fair summary of your analysis? Okay. Okay, and I'm going to give you the empirical trend. And then I'll admit that, like asking this question when I did is kind of a little bit of a red herring. Because as it turns out, and this is just why these types of questions are complex and organometallic chemistry is complex, sterics turns out to be the dominant factor here as opposed to electronics, even though I asked this question right after cruelly asked this question right after discussing back bonding ad nauseum. And how do we know that sterics is a dominant factor? Is that this is almost the exact same trend as if we were to look at the cone angle. And cone angle we will describe later lecture, but it is a proxy for, or it is a parameter that reads out how bulky a ligand is. So if there's a couple comparisons that you make here, so let's talk about sterics. So a triphenylphosphine versus triphenylphosphite, you have this intervening spacing atom. So the steric bulk of the ligand gets pushed farther away from the metal center in a phosphite versus a phosphine. So that's why triphenylphosphine is so far on the right. And then with within the phosphite series, you're comparing sterics and electronics as well. If you compare an alkyl versus an aryl groups can be a little tricky. They're often not as sterically bulky as you expect them to be at first glance because they have this ability to be able to rotate out of the way a lot of times and put their steric bulk in a way that's non-clashing, whereas alkyl substituents often don't. We have this discussion of back bonding, and indeed phosphites as a general trend are better back bonders, better pi acceptors than are phosphines. And then within the phosphite series, the more electron poor the R group is, the better it is going to be as a pi back bonder. So you've got sterics and electronics. Depending on which frame of thinking you're using, you can come to different conclusions. And I think, again, you weren't provided any data, so it's just a thought experiment. I think you thought it through reasonably. Yes.
One question, how do you compare the sterics of 2 and 4 to just to a value for the ligand? Like based on this trend, the sterics of 2 may be higher than 4, like the steric bulk within.
Yeah, this would be hard to, are you asking how you would actually test it, or how, if in a thought experiment, how you should think it through? I think you might not know.
I was just thinking if sterics is the major like affecting parameter here, then would it be more reasonable if you have 4 with a more steric bulk being having a lot larger KT than 2?
I think in general, an unhindered, i.e. non-ortho-substituted aryl group is less sterically bulky than an isopropyl group.
In terms of A values, those are probably similar, but then if we're looking at Cohen, it's probably something slightly different.
Right, and partly this depends too, like if you think about what these complexes actually look like, every change you make to this group, you aggregate 3 times per ligand and then 4 ligands per metal. And so I think aryl groups in this type of experiment end up having a smaller effective steric imprint because they can rotate in a sterically minimalistic conformation.
Can I ask
Yes,
a question?
Engle.
Do you see like a different trend if you use a bigger metal, like way different
Oh,
planar?
good question. What would you expect?
I would expect that it would change to make the electrons more important. Sterics would be more outweighed.
You would likely see a different trend, and you'd also likely see a different trend if you were talking about nickel, but maybe talking about nickel in a different oxidation state. So the purpose of this particular question is to just get you thinking, not to get to the answer. That I'll put that out there. And this wouldn't be similar to a question that we would ask on an exam where things should be more cut and dry. Okay, let me just get through these last couple notes. About ligand substitution. So now we're in business. We're doing work on the map. So swapping out one ligand for the next, for a new ligand. It can happen by different mechanisms. We're going to cover two, associative and dissociative. Which is the operative metal depends on a number of factors. When you're dealing with a 16 electron complex, so some here are familiar friends, palladium 2, platinum 2, rhodium 1, etc. These D8 square planar metals. Often you're in associative ligand substitution mode. Why is it important that it be a 16 electron complex? Associative ligand substitution effectively, a metal's coming in and then different metals going out. So the metal ligands coming in, different ligands going out. So the metal needs to have the ability to accommodate an additional ligand. It can do so if it's 16 electron. It cannot do so if it's 18 electron. So that's what's going on here. If you drew out an associative, so some of the stuff you can remember these rules, or you can just think it through. Like if you tried to draw out an associative ligand exchange mechanism on an 18 electron complex, you would need to go to a 20 electron species. You would immediately recognize that that is unstable and you would shy away from doing that. But there are exceptions, like any rule or like any empirical trend, there are exceptions. So here's an exception. This CP rhodium this carbonyl complex is known to proceed. I'm giving you the information that proceeds through an associative ligand exchange mechanism. And I'm asking why, how that could happen. Yeah, Eugene.
You get slippage of the cyclopenyl ligand from A to 5 to A to 3.
Beautiful. So you start out A to 5. Eugene's invoking a slip to A to 3. What is a slip? What does that actually look like? That means that for some reason I lost the ability to write in black. So a slip means this is effectively going to be an allyl ligand plus an olefin. So I'll redraw this in slipped form. What that does is it effectively opens a coordination site. So we draw open coordination site at the box. That allows triphenylphosphine to coordinate. And then to get to its stable form, it goes back to A to 5 and extrudes CO. If you want to accelerate this further, you can take advantage of an effect called the indenyl effect, first documented by Solo, now many decades ago. And that is that if you have indene, it's especially prone to undergo slippage because you do not need to disturb, you can maintain aromaticity of the second ring when you invoke this ring slip. And so this has a huge benefit in terms of the rate. It gives you 10 to the 8 in terms of the rate constant. And then the other flavor, and this is where I'll end, of ligand exchange is dissociative. And dissociative ligand exchange is normally what's taking place with coordinatively saturated 18 electron complexes. And the reason for that is somewhat self-evident because you don't want to go up to 20 electrons or too many electrons on the metal. So you first lose a ligand and then you find a ligand. And the most common way to diagnose which mechanism is operative is to look at the rates of ligand substitution. In a dissociative mechanism, the slow step is loss of the incoming ligand and coordination of the ligand is fast. In an associative mechanism, the initial bimolecular collision is the event that is rate determining. And so the consequences of that are that you have a rate law that is only has order in the metal ligand complex starting material in a dissociative pathway, whereas in an associative pathway, you have positive rate order dependence on both the incoming ligand and the starting complex. Furthermore, in a dissociative pathway, sometimes you will even get negative order in the concentration of outgoing ligand, which is a way you can double check which mechanism is operative. And there's some parallel, although this is not a perfect parallel, some parallel to classical nucleophilic substitution reactions in the main group, namely SN1 and SN2 in comparison to dissociative and dissociative respectively. Okay, so I'll stop things there and we will pick things up next week. Happy to stay after if folks have any questions.